Hello, and welcome to the design of a shell and tube heat exchanger for the cooling of the MSU Computer Center. Report done by Ian Wagaman and
Amy Griffin.
The purpose of this is to cool computers of the High Performance Computing Center at Michigan State. A proposal done by the Office of Infrastructure, Planning and Facilities was to use drinking water around campus instead of a refrigeration unit. The goal of this project was to design a shell and tube heat exchanger that can 1. Use drinking water as cold fluid, 2. Has food safe hot fluid, and 3. Must be able to extract 1 megawatt of thermal energy consistently while running. But the real question of this project is that possible?
In order to start our analysis, these are the parameters that we have to follow. Basically, we need to have a heat transfer of 1 megawatt, and our incoming temperature of the water is 57 degrees, and we need to keep the outgoing temperature of the water under 60 degrees Fahrenheit. So starting with our calculations, we did the mass flow rate, then see the cold fluid, and entering into the heat transfer equation at the bottom, this leads to a necessary temperature of the cold fluid out being 66 degrees Fahrenheit, which is greater than the goal of 60 degrees Fahrenheit. So we can conclude that under the conditions given, there is no possible solution. Therefore, we calculated the maximum heat transfer possible, and that ended up being 0.306 megawatts, which is about a third as much as I really need.
To design the system, we used ethylene glycol 50% for its food-safe properties and heat transfer abilities. We then insert the temperature in, and the program, based on all the other given parameters, gave us the final temperature of ethylene glycol and also the amount of heat exchanged. An important note is the heat exchanged in the program is 98.28% of the ideal calculations. Here are the design parameters for our heat exchanger. An area of note is the pitch, where there is a constant battle between a low pitch for a high number of tubes and a high pitch for a low buildup. The ideal pitch that we found was 0.9375 inches per foot.
So in conclusion, we found that our initial conditions did not lead to a possible solution, and that the maximum heat transfer possible was only about a third of the goal. But if we wanted to get 1 megawatt of thermal energy transferred, then we would either need to place multiple heat exchangers in series or allow the exit water to be over 66 degrees Fahrenheit. But assuming that the 1/3 of the goal heat transfer is sufficient, we still designed a shell and tube heat exchanger using ethylene glycol as our hot fluid, and Aspen calculated a total cost of $511,029 for the one heat exchanger.
No.
Thank you.